first like to thank the organizers and especially Ara for inviting me. Thank you very much. Very happy to be here. So Stefan has given a fairly detailed prediction for the Kondo temperature distribution at the Anderson transition. And my goal will be to try to convince you that his prediction is correct by presenting numerical evidence, focusing particularly on two aspects. One is that there is a power law tail in the distribution of Kondo temperatures, and that the power is related to eta, the multifractal exponent. So, simulations have been done in the Anderson model. I think everyone is familiar with the Anderson model, probably, so I won't labor that. So in d greater than 2, we have a transition. It's diffusive for small disorder, so W is this parameter which determines the amount of disorder. For weak disorder, it's diffusive. For strong disorder, it's localized, and there is a critical value of disorder where we have the Anderson transition. Here's some plots of wave functions. You have, for weak disorder, a wave function which is spread over the whole system. For strong disorder, you have localized wave functions, and then you have this multifractal wave function at the Anderson transition. Now, I'm going to be talking mostly about Kondo temperature distribution at the Anderson transition, but we've also previously looked at other distributions at the Anderson transition. One of them was the conductance. So you take an ensemble of cubes, and you calculate for each cube the two-terminal conductance, and you expect to get, in Anderson localization, we normally think that everything will be a function of the system size divided by the correlation length, or the localization length. At the transition, that goes to infinity, and you end up with a scale invariant distribution, which looks like this. This is something I studied together with Peter Marcos and Tomi Otsuki already more than 15 years ago. Another well-studied distribution is the distribution of the intensities of the wave function. So you have, it has this multifractal form. So if we look, we define this variable alpha. Again, there'll be some confusion about alpha. Alpha here means this, and in some parts it means the exponent. So this variable, this random variable, and you look at its distribution. You look at different parts of the distribution. So here we have a single wave function. I plotted 80% of the density. You look at different parts of the distribution. You see that it fills space differently. I mean, some parts fill space rather very sparsely. Some parts fill space more completely. That's the essence, for me at least, of multifractality. There is this distribution of, this is taken from a paper by the group of Rudolf Romer. And we have a distribution of alpha, which has this form. This f of alpha is what's called the multifractal spectrum. And one of the key assumptions, I think, in Stefan's approximations in Stefan's work is that this is parabolic. And as you'll see, it's not exactly parabolic, but it's a rough approximation. It's a good place to start. And you can, now you may notice that this distribution is size dependent, but just let me mention that it's possible to make it size independent by coarse graining and then working with a constant ratio of the box size to the system size. And then you can get a nice size independent distribution from that. Okay, I think Stefan has already explained the Kondo effect, so I'll go straight to the numerical work. So we have an exchange coupling. That's J. That will be an important parameter in the numerical work. The Kondo temperature will be found by solving this equation. We have this Tanch function here, which is peaked at EF. You have a local density of states. The local density of states looks like this. You have the wave function amplitudes, density of states factor, includes all the levels. And notice that we have to integrate over all of the states. Okay, we have a single impurity. So let me be clear. We have our disordered system. I imagine I put one magnetic impurity in it, and then I'm asking what's its Kondo temperature. So no. So I'm ignoring completely the fact that there are actually maybe interactions between different impurities. That's not the problem I'm trying to solve. Okay, so the local density of states has a lot of structure. I plot here a small piece of it. We need to integrate over the whole band, and the level spacing here is 10 to the minus 5. So if we were to blow this up, you'd see even more fluctuations, but these all need to be taken into account. Before getting into my own numerics, let me mention other people's. There have been previous attempts to look at this. Stefan has worked on this before, comparing, I think the main work here was looking at random matrix theory, but there were also some simulations of, so this was in 2006, some simulations of the Anderson model in 2 dimensions for relatively small lattices, 20 by 20. You can see there's a kind of bimodal distribution which appears. There's also a more recent work by Stefan and Hunyong Lee. Again, I think the main focus there was graphene. Is that correct? Both. Mainly, the focus here was on 2D and also looking at RKKY. Again, for RKKY, fairly large systems were studied, but for Kondo temperature, there are fairly small systems, 40 by 40. But again, you can see that strong disorder, there is this bimodal distribution and some kind of power law appearing. There's also this work, earlier work from 2006, so that's a more recent work. This is from 2014. This is a paper from 2006 by Cornaglia et al. They have not simulated at the Anderson transition, though they've gone from the metal to the insulator. The system is relatively small. It's a 13 cube lattice with 1,000 samples. You see power law. They claim to see power law behavior. I will come back to this graph in a little bit later. Okay, now let's look at Stefan's prediction. Okay, this is the full distribution that Stefan predicts at the metal insulator transition. Okay, there's a power law tail. This is what we're trying to find for low TK. The exponent eta is related to this alpha 0. We know the value of alpha 0, so we'll know the value of eta to expect. It's valid in this range, so roughly up to the level spacing and below the Kondo temperature, and I think the factor there is probably about half. Is that, say, half the Kondo temperature? So from about half so TK0 is the Kondo temperature of the clean system without disorder. So you go from about, say, half of that down to the level spacing. We expect that this distribution will be okay. So the value of eta is again given by alpha 0. We have some expression for the fraction of free moments. I'll maybe talk about that a bit later. Now, we want a method of calculating the states. We will use the kernel polynomial method. I think there was some explanation yesterday about kernel polynomial method. This is ideal for our problem because we want the local density of states at all energies, but at one point. And this is exactly what we get from the kernel polynomial method. Basically, you have an expansion of the local density of states in terms of Chebyshev polynomials. This expansion is convoluted with a kernel function. One has a choice of different kernels. The usual one, the most popular one, is the Jackson kernel. It's basically Gaussian-like with a width which varies depending on which energy you're looking at. But if you're looking at the center of the band, it's basically pi over m, where m is the number of moments in your expansion. So this energy scale would be important for the numerics. It sets a kind of lower limit of the Kondo temperatures that we can resolve in the simulation. So simulation parameters. Okay, we're doing cubes. We're going to put the Fermi energy at the band center. Obviously, we'll have the disorder set to the critical value. The exchange coupling, I've looked at two values, basically 1/3 and 1/2 of the bandwidth. So, energy scales. Okay, we have the Kondo temperature in the clean system. D is the bandwidth. This is the number of levels. So this is the level spacing. There's the KPM broadening. Eta KPM, not to be confused with eta. The expected power law range is this. So we need to make sure, basically the lower limit for what we can study will be set by the system size. And we need to make sure that eta KPM is at least as small as delta. We could make it smaller, but there wouldn't be a lot of point because we would start looking at mesoscopic effects. And it would be outside the range of the temperatures that we're trying to resolve. So we take eta KPM roughly equal to delta, or slightly smaller. Now, the KPM is an order n method, but we have L cubed sites, so that gives me an L cube, and I need to increase the number of moments, because I need to keep eta KPM with this, so I'm getting something that basically scales as L to the 6th. Now, if we go back and look at these energy scales for the previous simulation that I showed from 2006, you can see that the range of Kondo temperatures that they would be able to fit to Stefan's later work would be rather narrow, rather restricted. You can see they have power law behavior, but below this limit, the power law should depend, in fact, on the exchange coupling and not be universal, shall we say. Okay, so we've used, we tried to do a bit better. We've gone, instead of looking at 13 cubed, we're looking at 64 cube. No, I'm not saying it's incorrect, no. Simply, because they have one value of J. They have one value of exchange coupling. In the mesoscopic regime, this slope depends on J. Yes, because they are below, most of the data is below this limit. In their simulation, size of the system is relatively small, and then you go below, you're below the level spacing. So you will see a power law, but it's J dependent, it does not involve eta. At least that's the prediction. Okay, so we've looked at 64 cube and 96 cube. This is the kind of time involved using 288 processes on the University of Tokyo Institute of Solid State Physics System B supercomputer. Here's some results. So, okay, this is for 64 cube, band center, J equals 4, bandwidth is 12, so that's 1/3. We're at the critical point. Okay, the clean temperature, clean Kondo temperature, calculated numerically, not estimated using the usual formula, is this. Level spacing is about 10 to the minus 5. We need about 1 million moments to resolve that kind of energy scale. So e to kpm is, as I said, slightly smaller. We simulated 100,000, roughly 100,000 samples, and roughly a half turned out to have non-zero Kondo temperature. And then we're looking here at a histogram of the non-zero Kondo temperatures, scaled to TK0, to the clean system Kondo temperature. You can see clearly the bimodal type of, well, there's clearly a peak here. I won't say bimodal, let's say a peak here. There's a broad distribution with the divergence near t equals 0. Okay, I think it's useful since if we want to look at this part, I thought it would be useful to change the variable. So I changed the variable to this, which gives you a distribution like this. So we take the logarithm of tk divided by tk0. And you get something like this. Here's the numerical data, the simulation data. Okay, our resolution should be about somewhere around here. So this data is getting beyond what we can calculate reliably, I would say, down here. But we should be okay up to around here. We're expecting that, so the red line, sorry, the blue line is Stefan's prediction. There are no adjustable parameters in Stefan's prediction. The red line is simply to show that the power law behavior. And you can see it's not perfect. It's certainly for large Kondo temperatures, as expected, the distribution is not in agreement with the theory. But there is a tail. And then the question is this tail in quantitative agreement with Stefan's prediction? And if you plot like this, you have the impression that it's not. Okay? I will come back to that. This is L equal 96. Let's compare it with that. Basically, it's the same. Here we have to reduce the number of samples because now we need more resolution. The system is larger because we have a smaller level spacing. I mean, that was the idea, to go to get more resolution. So we need a larger number of moments. Consequently, even though we simulated for much longer, we have about half the number of samples, or 2/3 the number of samples. For these, again, about half are non-zero. You get a similar distribution. Again, fitting to Stefan's result. Now we're going, instead of being stopped around here, we're now able to get down to, say, here. A little bit better. Okay, changing J. Going back to 64, changing J. Again, similar structure. So the distribution now has changed slightly because we have changed the exchange coupling. This is the comparison with Stefan's expression. Again, by eye, one feels that the slope is a bit different from the prediction. However, I think analyzing this sort of problem is actually quite tricky, and I learned a lot from looking at this paper. So, Closet et al. Have written quite a long paper on how to analyze data which you think obey power law distributions. And they came up with this, what they call a recipe for analyzing them. So one first has a parameter x min. I'm afraid there's another alpha. It's a different alpha. Later it will be beta. Okay. So you think you have a distribution which obeys a power law which for large x decays as x to the minus alpha. And that this distribution applies to data for x greater than x min. So first you need a procedure for estimating x min and estimating alpha. You then need to calculate the goodness of fit. That's quite involved. It involves a Monte Carlo simulation, which for our data takes 1 day, just to calculate the goodness of fit. And you shall see that the results, unfortunately, are not very satisfactory. The third step I haven't yet thought about, but I'm mostly focusing on the first two, comparing with alternative distributions. Now, I found this table quite informative. So what they've done here is a test of their method. They analyze a lot of different data, but using their recipe. And to test their recipe, they generated data, know the power law, and then try to recover the correct value. Now, you'll see here various methods. You can ignore this column. This is for a discrete case. We're not in the discrete case. We're thinking about the continuous case. So we're looking at this column. The true value because they've generated synthetic data with alpha 2.5, so they know the true value, can be compared with these other values. Now, probably this is the one to look at. This is least squares. LS here means least squares. This is PDF, means probability density function. And, you know, doing what you make a histogram. You could think of this as make a histogram and then fit a line to the histogram. You get 1.4, which is quite clearly wrong. So one needs to be careful in fitting this kind of data. One can sometimes get in some case, working with a cumulative density distribution function, one gets a reasonable value. But working with a PDF, even with logarithmically scaled bin size, seems not to be advisable and leads to results which are simply wrong. So you'll see here this MLE. This is maximum likelihood estimate. Now, it turns out that if you think about this problem, and they did carefully, one does not need to do any fitting in order to estimate the power. You simply maximize the logarithm of this probability for your data, and you arrive immediately at this formula. And you simply calculate the maximum likelihood estimate of the exponent from the data without any histograms. Now, you need a way of choosing x-min. So what do they recommend for that? They say to choose x-min so that the Kolmogorov-Smirnov statistic, which measures the deviation of the data, so S of x is the cumulative density function of the data satisfying x greater than x-min, and P of x is your actual, P of x is the power law, and you're going to check how far you are from that using this KS statistic. And then you're going to choose the value of x-min, which, according to this statistic, gives you the best fit. That's fairly straightforward. The difficult part, numerically, or I won't say difficult, but more intensive, numerically intensive part, is this. You need a p-value, a goodness of fit, to check if what you've done is if your fit is at least reasonable. So to do this, they recommend fitting the original data and getting your x-min and alpha. Then you generate synthetic data sets, and here's where the complication arises. You have a power law region, and you have a region which doesn't obey the power law. So you need to generate appropriate random numbers in the power law region, and you sample with replacement in the region from the original data in the region which is not covered by the power law. You generate lots, you fit them in the same way as here, and you compare the KS statistic with the distribution of KS statistics you get here, and you get a p-value. Okay. Applying their procedure to our data, I think this is data for j equal 4. This is what we get. So now I'm using beta instead of alpha. We have 1.353. Have an x-min, which is roughly in agreement with what Stefan was predicting. Okay, for the exponent, it looks reasonable. The fit also looks reasonable. But p-value is 0. Now, this is a work in progress, and thankfully it's progressed quite a lot this week, but it's still unfinished, so I can only tell you what I think is the reason for this small p-value, and that will be evident here and on the next slide. So in Closet et al. Have provided us with the software for doing this kind of fitting. It's very convenient, but it assumes that all the data fit this distribution, whereas our data will fit not this distribution, but this distribution. That is, there is also a maximum. Oh, I forgot to, perhaps I've changed the variable again. This is now tk0 divided by tk, so I can work with large values instead of small values. Sorry, I should have mentioned that. Now we need to incorporate, and unfortunately, although the work progressed quickly this week while I was here, unfortunately, I was not in time to show you the results for incorporating this maximum. So the maximum likelihood, there'll be a maximum likelihood estimate. The formula is a bit different, involves a root finding, but it's basically, again, straightforward. After that is implemented, I hope that the p-value will become satisfactory. You can see what's wrong probably more clearly by looking at this plot, which is used by their software. So this is the probability that for x, which is tk0 divided by tk. This is a logarithmic scale here, and a logarithmic scale here. This is the fit. This is the simulation data. You can see that we have a significant number of samples which go beyond the level spacing and which are not expected to obey Stefan's prediction, and quite clearly do not, which is the reason for the, I believe, for the 0 p-value. Nevertheless, we have what 3 to 4 orders of magnitude where it's not so bad. This is the other case. This is j equals 6. This is, okay, this is tk0 divided by tk. So clean system Kondo temperature divided by Kondo temperature. Yes. This is L equal 96. This is L equal 64. And here's a summary. Now, J, you have here system size, you have here the exchange coupling. Okay, this is not so important. The value we are really focusing on is beta. And the predicted value, if we assume the parabolic approximation is 1.348, at least for the smaller system sizes, we have values which are close. We still have some system size dependence. Have a slightly smaller value for 96. I should say that if we go beyond the parabolic approximation, though the parabolic approximation seems to be quite integral to Stefan's calculation, it's not just, but if we just imagine forgetting about the parabolic approximation when we calculate eta, then, I mean, we can use the parabolic approximation to get eta from alpha 0, or we can look at the actual f of alpha and get eta from that, and you have a slightly different value prediction. But surprisingly for me, for larger system sizes, it actually seems to be approaching this value. Okay. Now there is still, here we have to remember that the goodness of fit is 0, so I need, next week I hope to address this problem and take into account the lower limit, which is, the upper limit here, which will be tk0 divided by the level spacing, and I hope that these results will still be valid. It remains to be seen. Another thing that Stefan predicts is the fraction of free moments. And this seems to be, I have to say, way off. We have prediction of 8%, whereas actually we found about a half for L equals 64. We expect to miss some because of the level spacing, cut off at the level spacing, but the calculation of that gives only about 1%, so that doesn't explain it yet. Probably deviations from the parabolic approximation might. Okay, so I'm going to summarize. We have a broad distribution of Kondo temperatures. The prediction is that there's a power law tail, and the exponent reflects multifractality. We don't yet have a confirmation of that. We have, I think, some evidence that it's probably right. I hope that when I have more time to work on it, that we'll be able to solve this goodness of fit problem and confirm the prediction. And we expect it to be observable in the temperature dependence of the magnetic susceptibility. Thank you for your attention.